Hey guys, welcome back. We're going to talk about solutions in this one. We're going to talk about solutions, what they're made out of, and kind of how it works at an entry level. So let's dive on in. Solutions. So solutions first, they can be in any phase. Solid, liquid, gas, right? Solid solutions, an alloy would be an example. Liquids, that's what we're going to deal with most of the time, especially in Gen Chem 2. And gases, like obviously air, perfect solution. All right? There's two components to a solution, as you probably know. You got the solute, and you got the solvent. All right? So the solution is made up of the solute and the solvent. So what's the difference? So the solute is the minor component. All right? That's the thing, the species that is dissolved. That or what is dissolved. Where the solvent is the major component. Right? What does the dissolving? All right? And now, we live here. Aqueous, where you have H2O, water is the solvent. We're going to be there a lot. All right? Okay. And so when we talk about this, solvent, water's a lot of solvents for most of our household stuff. All right? At the house, you look, most of your stuff's water. Now, there are things that water's not the solvent, especially if you deal a lot with oil-based paints, or hydrocarbon compounds. Those, they have different solvents for that. All right? And there's lots of them. Now, when we talk about how much dissolves of the solute, so like how much salt can you put in the water, right? How much dissolves? Right? And typically that question is answered by solubility. Right? Which it can be in grams per it could be grams of solute per grams of solvent. It can be in molarity. Right, that's a horrible molarity. So grams of solute, grams of solvent could be molarity, grams per liter, or moles per liter. Excuse me. Right, it could also be grams per solution, grams of solvent per grams of solution. Right. So for example, sodium chloride at 25 degrees Celsius, you have, 36 grams per 100. All right. So as you can see, this is temperature dependent. All right, and you guys know it's temperature dependent. If you make, I live in the South and they like their sweet tea. Well, you can put a lot more sugar in hot tea than you can cold tea. So they make their sweet tea hot and they cool it down, and there you go. If you like sweet tea. Now there's 3 words we can generalize how much solute is in a solvent. You can be unsaturated, saturated, or supersaturated. All right. If we are unsaturated, more solute can dissolve. If we are saturated, right? If we are saturated, right? That's the maximum amount of solute, right, is dissolved at that temperature. And supersaturated means more solute dissolved than the max at that temperature. Right? So you have your concentration is above the solubility. All right? These are typically unstable. Right? Typically they're not stable, all right? And if you disrupt the solution, a lot of times solvent will come out of the solution, or solute will come out of the solution. All right? So, and we've all made solutions at home. So this is not new, we're just defining it. Now, when we talk about on the chemical level making a solution, right? A lot of times we call that solvation. Right? The solute gets solvated. And this is the process by which solute molecules are surrounded by solvent molecules. All right. Now, the question then is, what determines if something will dissolve? Right? A compound, a atom, or whatever it is, right, will dissolve. Right, that's the question. Good question. And the trend, of course, is, hopefully now know it's intermolecular forces. Intermolecular forces. What are the three interactions? Right? So when we have, there's three interactions. Right? We have the solvent has intermolecular forces with the solvent. The solute has intermolecular forces with the solute, whatever they are. And then the solute can have intermolecular forces and interaction with the solvent. Right? So there's three interactions. Okay? And if the solvent and the solvent here, if this interaction is way bigger than this, or this interaction is way bigger than this, they're probably not going to dissolve. Right? That makes sense. However, if they're similar, right? If the solvent is similar to the solute, most likely this happens. Okay? So it happens. Now, it's a 3-step process. Right? It's typically exothermic. Typically, it's a 3-step process. Which means what? So if exothermic, that means heat's leaving. Now, that's not always the case, right? The first thing that comes to mind is those instant cold packs. You break something, right? Typically, you're breaking. They used to be like ammonium nitrate. I think it was ammonium nitrate. But it was a compound that when it dissolves in water, it absorbs heat. It's endothermic. I mean, I don't know what they are now. It's probably something much safer than that. But they're one. That's why they're one use, right? They break, the compound goes into the, dissolves in water, and it absorbs heat. Okay. Most things, when you put them in water, though, release heat. Energy is released, right? Because if energy, it means it's more stable, right? If energy is released, it's more stable. It's energy favored. All right. 3 steps. First step. First step would be the solute particles have to separate. All right. So whatever the solute particles are, whether it's sodium and chloride, whether it's sugar molecules that are like being, interacting with other sugar molecules. Like if you're putting sugar in your coffee or tea, right? You got your, if you're using sucrose, what is that? C12H2O11, right? And they're interacting, but there's a bunch of them there, and so then they separate. They got to separate, and that has energy change associated with it. 2, the solvent particles have to separate. That also has energy, right? Okay, because you're breaking bonds, requires energy, right? And then 3, the solvent and solute mix, all right? And that also has an energy associated with it. And so the enthalpy of the solution, usually H2SOL or SOLN, would be equal to the 3 steps added up. All right. And the key word here is mix. All right. The mixing. All right. And so that leads us to the driving force. The driving force, which is a lowering of the system's potential energy, right, is due to entropy. All right, new term. We're defining it kind of early. We have a chapter coming up on it, but entropy. All right. And so what is entropy? Good question. So entropy is how dispersed right, or spread out the system's energy is. Right? Which means, right, these solvents and solutes, they mix, or what we call dissolve, to become more stable. So typically things naturally mix to become more stable. So if you're a soda drinker, there's lots of things in soda, but we'll pick on 2. We'll pick on the sugar in soda, right, which is C6H12O6, right, high fructose corn syrup usually in this country. And then they put carbon dioxide in there. if you drop the soda, one of those comes out, right? The carbon dioxide comes out of solution, right? And it can make a mess. The fructose does not come out of solution. The sugar stays right on in there. All right. So why? Well, typically, right, like intermolecular forces, dissolve or mix with, right, like intermolecular forces. All right. So what are, right? We have hydrogen bonding, dipole-dipole, and we have London dispersion. Right? So we have the polar side and the nonpolar side. All right, so typically polar things, right, ionic compounds fit in there, right? Typically they go into water, which is polar, and typically nonpolar things like carbon dioxide will not go into water. So this is why if you get sugar or syrup on your hands, hot water, it's pretty much gone. You don't even need soap. But if you get olive oil on your hands, you're going to need soap because that hot water does not take it off. Not like it does with soap. You'll need the soap. All right? And so, two words, miscible and immiscible. Well, miscible means they mix, and immiscible means they do not mix. All right? That kind of makes sense. All right? So, the general rule like dissolves like. So if I'm a polar compound, I typically will dissolve in a polar compound. If I'm in a nonpolar compound, I typically will dissolve in a nonpolar compound. Ionic compounds typically will dissolve in polar compounds like water, but not all ionic compounds do. There's more to that story, right? Sodium chloride obviously does. Calcium phosphate does not. Chalk, right? Calcium carbonate does not. Right? If you have sidewalk chalk, right, or even magnesium carbonate, the gym chalk, it doesn't really dissolve in water. Okay? I mean, we're going to learn later on in Chem 2 that a small fraction does, but that's a tiny fraction, not most of it. Over 99% of it does not. Right? And so if you have sidewalk chalk, you wash it off, right, because it's not chemically bonded to the sidewalk, but you're not dissolving the chalk. All right, so that's kind of how that works, right? So let's take a picture of this. Let's get a picture of this, right? You know, sodium chloride in water. So we have NaCl, right, solid, and we're going to add that to H2O liquid. All right, what happens? All right, what happens? Well, you have your sodium chloride together, Na and Cl, and it's a solid. We just usually draw an arrow, and you get Na plus with the state symbol and Cl minus with the state symbol. All right? But there's actually, right, and there's delta H as solution here. And we'll put the solvent on the bottom so you know. All right? And so there's an overall energy change. All right? Now, sodium chloride is a solid. It's actually got to break up, right, to Na plus and Cl minus. All right? Now, this process is how we as humans describe it. It's not right? You're not going to see this happen. But how we define things, we'll put a G there for gas. You're not going to like, oh, my sodium chloride. Oh, I see the gas, right? That's not what happens, all right? But how we calculate this, right, in our steps, right, this step to break up sodium chloride from its crystal lattice to free ions, right? Right? We have a process called that, and that would be its lattice energy. The lattice energy, right? And that's the energy required to break up the crystalline lattice. Right? So it's got to break up. Right? And it takes energy to do so, right? Because the lattice energy is the energy released when these ions form a lattice. So when sodium chloride get in their crystal structure, energy is released. It's more stable, right? And so to break it up, it requires some energy to pull those sodium ions and chloride ions apart, right? But then, over here, you have the solvation energy. Right? Which is the energy released when the ions are solvated. All right. So what's a hydrated or solvated ion? Now, the picture we're going to draw works for little ions, right? Obviously, you have a big molecule like sucrose, C12H22O11. That's a much bigger molecule than sodium ion. Sodium ion's tiny, right? It's a tiny little cation. Even chloride's kind of small. So what water does with the one ion is different than if you have a bigger molecule. But anyway, we got sodium ion here. And we'll have chloride over here. And we're going to make it, well, that's too big. Not to scale. All right, not to scale. But their sodium is much smaller than chloride. And so what happens is you have, water has its hydrogen bonding network, right? And so you got your water, HOH, HOH, and this is in 3 dimensions, right? And you have your hydrogen bonds between the water molecules, right? If that makes sense. On these lone pairs, right? Hydrogen's bonding to other waters adjacent to it, right? So it's those hydrogens are interacting with another oxygen from another water molecule, right? And that makes this nice, tight-knit hydrogen bonding network. Well, when you put this cation in here, hydrogen and oxygen kind of arrange. And if you think of it as like octahedral. So for octahedral here, I'm going to try to draw octahedral the best I can. Same thing with chloride. Same thing. I don't know if I'm in the middle or not. So we kind of got it in what you would think of an octahedral. It's probably too high in the chlorine, but we'll go with it. So when we got water, if we look at H2O again, the negative side is by the oxygen, right? The delta negative. That's a horrible delta. Sorry about that. I'll try that again. And the positive side is over here, right? Water is very polar. This is a polar molecule. Well, the negative side of water is going to be around the sodium. And the positive side of water will be around the chloride, right? That kind of makes sense, right? Because of the charges. And so what we get for water is the O is there for the sodium, right? O is surrounded. So a lot of times I write it as OH2, right? Either H2O like that. So you know that the oxygen is around, right? And there's usually 6 in this inner solvation sphere. Chloride is the opposite, where you have the oxygen and the hydrogens like that. So you'd see it OH2 here. All right, so that's how we differentiate which way. Hopefully that makes sense to you guys. So this then gives us in 360 degrees water now oriented this way, which then makes your hydrogen bonding network different, and it makes it different over here, but it's neutral, so it works out. But those are solvated ions. All right, so that's kind of what happens. There's kind of 6 water molecules on the inner solvation sphere, and then there's another layer of water oriented because of it, and then you get out to back to the regular water. So water obviously can only hold so much of these ions before it can't hold anymore. All right, which then is, how can it hold more? How does it hold less? That leads us into factors affecting try that again. Solubility. Factors affecting solubility. We've already talked about one, and that is temperature. Another one is pressure. So let's talk temperature first. So typically, again, these are generalities. It doesn't mean everything's the best or everything follows it perfectly. It's not perfect, but it's generally. So typically, right, as temperature increases, let's go with the one. As temperature increases, more solids can dissolve in liquids. Right? Which means solubility increases. Right? So again, hot water, typically, like this is why you use hot water for dishes, right? And some of you can use really hot water. Some of us, I don't use it all the way hot because my fingers do not like it all the way hot. All right? And some of us don't mind that. But the hotter it is, typically the more dissolves, and typically faster dissolves too. Typically dissolves faster and more. So when you're doing dishes, the hotter the water, right, the more it dissolves. Dishwashers, hopefully they get the water really, really hot, and that's why dishwashers work as well as they do, right? Or some of you don't trust the dishwasher and use it by hand anyway, but that's a different story. Now, the other temperature dependent is for gases, typically, right? Less gas dissolves in liquids as the temperature increases, right? Solubility tends to decrease. So, for example, if you have a soda, if you're a soda drinker, if you have a warm soda and you open it, more of the carbon dioxide comes out than if it's a cold soda, all right? That's just how that works, all right? So unlike if you want more sodium chloride, if you want more sugar in something, hotter is better. If you want more carbon dioxide in something, colder is better. Now let's jump over to pressure. Pressure affects the solubility of a gas, right? And this leads us to Henry's law. Henry's law. And that his law is as the pressure of a gas above a liquid increases, the solubility of the gas increases. Let's put in the liquid. So going back to soda, right? They are bottled under high pressures of carbon dioxide. Right? There's a lot of pressure of carbon dioxide over the soda. It doesn't have to be the whole environment. They can, they have their techniques. You can probably look up on YouTube how that works. But that's what happens. You have more pressure of carbon dioxide above the liquid, more will stay in the liquid. All right? That's Henry's law. So what is actually Henry's law? S, horrible S. Let's try that one more time. S equals K H times P. So what do we think these are? S would be solubility. P, of course, is pressure. K is the Henry's law constant. All right. Depends on the gas, solvent, and temperature, which is fun. So they're actually very easy problems in this course. You would have to you're either given K. Most of the time you're given K for the solvent. You either find the P, the pressure, or you find the solubility. And that's it. All right, so that is solutions, the overview of how they form, why they form. And we'll see you next time, guys. Let me know if you have any questions. Take care.